Hey, this is Dr. Della Corte with Physics 313R, Introduction to Quantum Computing, Lecture 2. Today we're going to talk about spin. All right, let's quickly review what is computation. So computation is the process of taking some input data, sticking it into a function or into a computer or some machine that crunches or manipulates it to then produce the final outcome or answer. Always this idea, an input is manipulated to produce an output. If you think about classical computers, there we have the smallest unit of input that can go into the classical computer is called a bit. And we talked about it last time. It's effectively a switch that can be on or off. And that small, so every type of information that you can put in a computer or into a function is made up of many of these bits. They get crunched and produce different bits as outcome. In quantum computing, however, the smallest unit is not just a switch that can be on or off, but it can be a qubit, which is this superposition of different states that we introduced last time. And today we're going to learn how this superposition can be physically represented, for example, in the spin or polarization of an electron. Great. So let's recap one more time. Classical bits are anything that can have two states that is binary in nature. A light bulb, for example, that can be on or off. You might say, well, maybe sometimes when you turn on the light, it kind of flickers and it's somewhere in between 0 and 1. Yeah, that is correct. But anyway, we consider light bulbs either on or off, and we don't worry about the intermediate time steps, right? So anything that can be on or off, a light switch, a light bulb, zeros or ones, those are representations of bits. So anything that can be in these two states is potentially a way to build a bit. Now, there's this really deep thought that is listened out here just in one line, is that all types of human logic and reasoning can actually be converted into mathematical equations that just operate with bits. And being able to mimic everything that a human does, even to a large degree, how a brain works. If you think about large neural networks, for example, like ChatGPT, that can do so many cool things, they're still all based on classical computers that effectively use very smart combinations of switches that are turning on and off in order to automate many, many things that humans need to get highly trained on in order to perform themselves. And so being able to represent everything that a human does through bits and some logic inside of a classical computer is really powerful. Now, bits are very small units of information, 0 or 1. So in order to put large amounts of information together, you have to group them. And so common ways of grouping them, if you go iPhone shopping or laptop shopping, you typically hear about megabytes or gigabytes or terabytes. So those are the typical units we deal with on our daily life. And so what actually is a gigabyte? So one thing you note is this word giga. You might have heard from measurements where you have a metric ton or 1,000 or a kilogram, or 1,000 kilograms is a ton, might be like a megaton. It's like 1,000 of 1,000. So giga would be 1,000 of 1,000 of 1,000. So you might have heard about these superlatives from kilo to mega to giga to tera, peta, and so on. Those are not ending on bits, though, they end on bytes. Byte is like this word creation that someone came up with. In my mind, it sounds a little bit like a bit and an eight being mixed together to create a byte. And a byte is effectively a collection of 8 bits. And that oftentimes is considered the smallest unit in your computer, but a byte itself is made up of 8 bits. Sometimes people also talk about nibbles. I don't hear that very often, but that sits in between a bit and a byte. One thing you might note is that the factor to go from one to the next in this pyramid is not a factor of 1,000, but a factor of 1,024. The reason is that 1,000 is not the exponent of, not an exponentiation of 2. So everything in the world of computers is always a 2 raised to something, and the factor 1,024 is just the power of 2. So that's what's being used. So when you have 8 bits, they make a byte, and then 10,024 bytes make a kilobyte. And then if you take 1024 of these kilobytes, you get a megabyte. And so if you want to calculate how many bits there are among them, you would have to multiply 1024 by 8, and that gets you the number of bits, which we don't really talk about often unless you think about internet communication, where people try to sell you megabits, which sounds like a byte, but it's actually a bit. So don't fall for the scheme. Okay, great. So let's talk now about qubits, the smallest unit in quantum computing. I'm trying to move my finger. So a qubit is powerful because it is not only in an on or off state, but it can also be in any in-between state, which we call a superposition. Mathematically speaking, a superposition is a linear combination of two states or more states. In this case, in a qubit, we have the on and the off state, or off is 0, on is 1. And then we say, well, there's a certain amount of offness here. So a certain amount alpha of offness plus a certain amount of onness beta. And what we do in these qubits is we say, well, this resulting vector here, we say that should only have a length of 1. So it should be normalized. So then alpha and beta will have some type of factor in front of them that makes sure that the length of this superposition is 1. And so you can imagine that this vector that could point to 1 or to 0 can also rotate around, and it oscillates around. It is sort of like a vector that sits in the center of Earth, pointing to any city on its surface, and you can point to any city on the surface of Earth. It's always the same radius of the Earth, but it can point anywhere. So over time, this vector will map out the entire surface of a sphere. And so what a qubit effectively is this spherical surface that allows you to be at any point on that surface of the sphere. Okay. Sometimes people talk about, well, this is like a dimmable light switch. We're somewhere between being on and off, somewhere almost on, or maybe it's really like a dimmable light that's like a little bit on. That's not quite correct. And especially once we start talking about quantum algorithms, we will see that this metaphor doesn't hold because it ignores the important fact that there's something called phase information in here as well. And the trick to building really cool classical quantum calculations, quantum algorithms, will be to manipulate these phases. We don't talk about that very much in introductory physics courses, but as you advance in your field, you learn about waves that go up and down. And you know it when you take two rocks and throw them into a pond, that the ripples that they are created can sometimes amplify each other and sometimes cancel each other out. And this idea that certain signals can be amplified while others can be canceled out is the fundamental idea behind many cool quantum algorithms that we'll get to know a little bit later in the course. Okay, but now to the question, if a bit can just be on or off, like a light switch, what could be a qubit? What can be this sphere where you can be in all types of states, but with certain rules and limits to it? It turns out that there are two really great ways of representing that. One of them is the spin of an electron. And we're going to look into spins in a little bit more detail in a second. The nice thing about spins is that they come in so-called quantized states. That means there are only two allowed values for a spin. We call them either up or down for an electron. And before you measure the spin of an electron, the spin can be actually any in-between thing, but only once you measure it, you either lock it into the up or the down position. And so a spin is a very natural representation of a qubit. A second phenomenon is the polarization of photons, where you can say that photons, so electromagnetic waves or light, can be polarized either vertically or horizontally. And if you separate them out in these vertical and horizontal components, then you can say, well, if I measure it, if I force them, for example, through a polarization filter, like your sunglasses, you will only let them through if they're in this polarization or that polarization. But before you force them to be anything, they can be randomly polarized and can be any in-between state. Okay, so those are two possible ways of representing qubits. Let's look at this idea of spin for a moment more. Here is the Bohr model of a silver atom shown. So you have the nucleus of the silver atom, and then this has 47 electrons that are filling up the orbitals around it. And if you had chemistry, you might remember the pairing rules and what it takes to calculate how many electrons are allowed in each of these each of these orbits. And what you find out is if you fill up your shells, eventually when you're putting your 47th electron on the shell, you'll find it sitting all by itself on the very outmost orbit. And when this electron is here, this one doesn't have a partner. All the other ones, they have partners. And so the Pauli exclusion principle that defines how these can be filled up says for each electron that can have very unique quantum numbers, each of these can be, for example, at the end of the specific state here with a spin up. That the next electron that you put in will be the partner that has then the spin down. And the two cancel each other's spin out, and so you can't measure it outside of the atom. But that one single electron that's out here, that one doesn't have a partner with it. So if that one happens to have a spin up or maybe spin down, then that might be measurable because there's nothing on this atom that can counteract it. And so the question was, what can we do? Oh, wait, maybe one thing we want to also review from physics is if you have a charged particle like an electron and it's moving around, it's a moving charge. And moving charges create magnetic fields. And so a magnetic field of this lone electron can give this atom also a small magnetic field. And that can make it slightly more polarized in one direction than the other one. And then it can start to interact with other magnetic fields. Okay, great. And so what we see here, just in a nutshell, we have the silver atom. It has a lone electron. That lone electron has a spin up or down, and it causes a magnetic field that is barely measurable. And we'll see why that is important. So for now, we just assume that when you have this silver atom, it is going to be approximated like a bar magnet, a very weak bar magnet that has a little bit of a south pole, a little bit of a north pole. Okay, so silver 47 in our mind is like a little magnet. And why do we care about that? Because there's a very famous experiment which goes like this. This is a bit annoying. So we have here a magnet that has a south and a north pole. So it's a permanent magnet. And you can see the south pole has a weird shape, which makes it so that the magnetic field is quite strong here at this tip, while the north pole is a bit weaker. And now we go ahead and we take a magnet and we let it run through that magnetic field. If you have a magnet that has a north pointing up and a south pointing down, the north pole will be attracted by the south pole and the south pole will be attracted by the north pole. But since the north pole is stronger attracted by the strong south pole here, you would assume this to fly up like that. No problem. If you would have a magnet that would be flipped around like that, you would assume that the south poles repel each other. Okay. If you would take the same magnet and rotate it like that and you would let it go, it would again get repelled, but maybe not quite as strong. Or if you have it twisted like this, it might get attracted by the south pole, but not quite as strong as the one that was horizontally oriented. So if we have random silver atoms that are like bar magnets and they can spin in space, right? There's nothing that forces an atom to be certainly oriented. So they're randomly in there, and you would shoot them through a strong magnet. You would assume some of them are parallel to the magnetic field and they get a strong reflection, or others they would be just slightly rotated relative to this magnetic field, and then they would not be so strongly diverted, but sort of form a pattern here. And maybe you would expect to see some type of normal distribution. Let me see if I can draw here if that works. So maybe, oh, pen, draw, pen. Yeah, maybe something like that. Let's try it again. Maybe you would assume a distribution, something like this. A lot of things will cluster in the middle and then a few things on the outsides. All right, good. Now, In the actual experiment, the following happened. This is the so-called Stern-Gerlach experiment. People produced silver atoms and then they shot them through such a magnetic field. And what they found is that the silver atoms hit a screen behind it, not according to what you might think the distribution would be, but just in two very distinct patches. They either behaved all like perfectly straight up or perfectly straight down magnets. And they formed just a cluster on top or a cluster at the bottom. And that was a huge surprise when that experiment came out, because that is something you would never experience in a normal laboratory setup where you have, at room temperature, large magnets or things that you can handle that are being shot through magnetic fields. Things do not behave so distinctly. These atoms that you would expect to form a distribution never formed a distribution. They either behaved as perfectly upwards or perfectly downwards aligned magnets. And so that's really, really surprising. So let's think about this. Why could that be? So if we have a magnet like that and it goes through here, it must somehow magically, mysteriously, in the magnetic field, interact with it in a way that forces it to become upward or downward oriented to then end up at a deflected path. And this weird wiggly motion that's going on there in the center, that is what we call this here. This is what we call a measurement. A measurement in quantum mechanics forces a randomly or somewhat randomly oriented qubit or spin in this case to be aligned perfectly with the axes of measurement, either this way or the other way. It's very strange, but that's the only explanation for the outputs. Somehow measuring it forces the spins in one or the other state, and that then causes this clear clustering at the top or the bottom. Okay. Um, So with the silver atoms, this works this way. Electrons behave the same way. Electrons have also the spin up and down. And so if you would send electrons through a magnetic field like that, it's a little bit harder to do that because electrons are charged particles and other things are happening too. But let's assume that you could do it. If you would send them through, you would see the North Pole here to be strongly attracted by the South Pole and all the electrons bouncing up here on the top. And if they would be the other way around oriented, then all of the electrons would hit the bottom of this, would come out of the bar magnet, of the permanent magnet, and end up being clustered at the bottom. Now you might ask yourself, well, this seems to make sense if I set up my permanent magnets from north to south, but what if I set them up from east to west? Or I just rotate the magnets? Well, what turns out is that you're going to measure spins, but they're going to be no longer up and down. Now they're going to be left and right. And so everything will be forced in the new directions of the magnetic field to either be on the right side or the left side of your permanent magnets. That is also very weird because this type of orientation was clearly not allowed when my magnets were pointing upwards. But in a moment where I change my measurement, there really seems to be something funky going on as the measurement takes place, which now informs the electron, hey, you can't be in this or this state. You have to be now in this state or that state. And then they come out such way. All right. So you can already kind of get a glimpse for the idea of orientation of measurement playing a role and clearly measuring vertically versus horizontally results in different behavior of the spins. So in order to get this correct, we need to introduce something called the angle of a spin. We call this theta, and it's going to be this angle that is measured from the vertical. So this one here might be a theta of 45 degrees. So if theta would be zero, then this qubit would be pointing straight up. And then we would say the electron spin points towards the north, straight up. Okay, great. Now let's introduce the quantum clock. This will be a model that we'll use quite a bit throughout the course, so let's give it this fair time here to introduce. The quantum clock is a clock that can't tell you what time it is, but you can ask it if it is a specific time. Those are two different things. So if you have a normal clock, you might ask it, hey, what time is it currently? Well, and the clock would tell you, well, look at me, I'm at 2 p.m. right now. It's 2 p.m. If you have a quantum clock, it looks more like this. You don't see the minutes and the hours, but you could ask it, for example, hey, is it 6 p.m.? Well, we knew before it was 2 p.m., so the answer should be no, it's not. But when you ask the quantum clock, it will tell you one of two options. It will either tell you, yes, it is 6 p.m., or it will say no, but not no, it's something else. It will say no, it's 12 p.m. You only get one of these two options. So conversely, if you ask it now, is it 3 p.m.? The answer the quantum clock will give you is either, yep, it's 3 p.m., or no, it is the opposite, 9 p.m. That's very, very different from normal behavior. Because if you have a normal clock, there's a certain time that's true and every other time is wrong. With the quantum clock, and you ask it a specific time, then either that time is right or the opposite time is right. Okay, so that's just going to be a mental model that we'll use a bit in the course. So let's go back and try to understand that. Um, Now we're going to go one level further. So let's assume we asked our clock, is it 6 p.m.? There are two options. It can either say, yep, it is 6 p.m., or it says, no, it's 12 p.m. Let's assume it says yes. Okay, now we know it's 6 p.m. What if we ask it again, is it 6 p.m.? And the clock will say, well, of course it's 6 p.m. You just asked me the same question twice. Yes, of course it's 6 p.m. Let's say, okay, well, how about 3 p.m.? Is it 3 p.m.? A classical clock would say, hey, what's going on with you? Something wrong in your mind? I already told you twice it's 6 p.m. But the quantum mechanical clock will now say, yeah, of course, it's 3 p.m. It's actually a 50% chance for that. So it's 3 p.m. Uh, but wasn't it 6 p.m. a second ago? Is it not 6 p.m.? And then I might say, no, it's actually 12 p.m. Don't you know what's going on? So that is something that can happen in quantum mechanics, and that is quite mind-boggling. So take a moment to understand this. We're going to keep going and try to make the connection here so you understand what the heck is going on. So if we bring this back to spins, let's say we have our electron that's oriented like that, and we send it through a permanent magnet. The north and the south pole, they attract each other, so all the electrons will collect up here. If we take all of these electrons and send them through another magnet, let's assume you stack the magnets behind each other, then this guy is going to run through the next one. And if that looks exactly the same, then they're still going to get deflected upwards. No change in behavior. But if you now, so 100% of these ones would now be still in this orientation. But now you take these ones and send them through a magnet that is rotated like that. Now you have zero information if that electron might be pointing towards the left or to the right. And so you end up with 50% of them going to the right and 50% going to the left. Now, if you take these 50% that went to the right and send them through the same magnet that you had initially, you will find that these ones have lost all of their knowledge of where they were before. And now you're going to get some of them coming up on the top and some at the bottom. And if everything is designed correctly, these will be 50% probabilities. So maybe 50% ended up here, of these 100% here. So 50 of the initial electrons. Then we had 25 of, so 50% of the 50%, 25% go here. And then another 25%, so 12.5% of them come out here. So the key point on this slide is that whenever we perform a measurement, we change the state. However, if you repeat the exact same measurement twice, then you will not change the spin again. Okay, but in a moment where you measure and then change the measurement, you keep on changing the spin. That's pretty cool. Now we might ask the question, is this idea of changing things through measurement a generally true statement? Does that also happen on the laboratory scale that we are more familiar with? So for example, if you have a ball, let's ask ourselves if measuring the speed of a ball is going to change its state, its speed. So we have a ball and we can throw it up and down. How could you measure its speed? Maybe you use some laser gates and you measure how much time elapses between the ball passing these two light beams, and you know how far they're away from each other. Now you have a time at which the ball crosses the first light beam, a time at which it crosses the second. You have the distance, so you can calculate the velocity. It's the distance divided by the change in time. Okay. However, what you might not often think about is in the moment where the ball is flying through that light beam, there are photons in that light that actually interact with the ball. And since the ball is really fat and these photons, they're very small amount of them, they don't really do anything. If you take the ball and make it very, very tiny, so instead of using a ball, if you think about sending a single atom through there, and if you have an atom go through there and it's getting hit by a photon, maybe that photon has enough momentum or energy or whatever to deflect the ball. So maybe something like this could happen. Could this be what happens with a magnet that flies through a different magnet? And is it just because we are not dealing typically with atoms and spins and tiny, tiny things that we don't observe this weird behavior of measurements messing up states? Yeah, it turns out that's not the case. People have tried this experiment in different forms, and they found out that the change of state to the electrons, to the spins, does have nothing to do with the intensity of the measurement. So you would assume that if you have a very strong magnetic field, you would gonna shift the orientation more around than using a weaker one. But just the act of measuring, independent of intensity, is going to give you this clearly gated signal. And that is just some of the weird things about quantum mechanics. So while we might have some intuition for why this could be the case, our intuition unfortunately is wrong. Experiments so far have shown that it's not related to its intensity, but simply to the act of measuring to define the final state. Okay, great. So takeaway from this is the measurement and in which direction you measure matters, but not the strength of the measurement itself. With this, we opened up the floodgates to true randomness. What does that mean? If I set up a single experiment with taking a magnet that takes a spin and separates it out, and then send that spin through another magnet, I'm going to have it come out either on the right or the left. So 50% on the right, 50% on the left. So if I would repeatedly do this, send these guys through, so just the first magnet to separate out the electrons that are deflected upwards and then deflect them through the second setup. And I could very quickly measure, will this electron end up to the right or to the left? I could take note of it and say, for example, the one turns out on the left, I call it the north one N, and the one on the right, the south one S. And I could get the string of N's and S's. And this type of N's and S's will form a truly random string. Right. So we get this completely random sequence of N's and S's. Well, is it truly random? So what if I take a coin and I throw it up in the air? Will it land with heads and tails totally random? Can I just create a random sequence that way? Well, if you think about, maybe you remember that from your introductory physics courses, the initial conditions of tossing a coin, the point where you hit it, the weight of your coin, the force with which you hit it, the angle at which you hit it, there can be very small changes in these initial conditions. And these small changes in initial conditions, they produce something that we would call pseudo-random. So if you keep on flipping a coin, it will look like a random sequence, but it's only because there are these um, microscopic changes in the initial conditions that you can't really perfectly control for. So they're not truly random. As a random experiment, that is random due to chaotic behavior that is triggered by the different initial conditions. Actually, a little study that came out a year ago where they found out that when you take a euro coin, they're not perfectly balanced. It's actually a slightly higher chance to land. I believe it was on the side that has the number on it compared to the, you guys call it the head side, 0.8% higher. So if you're into stock market or whatnot, if you would get stock markets with 0.8% chances right all the time, you would could get infinitely rich. So that's high enough for it not to be considered truly random. Okay, cool. But spins, we think, are 100% random. Now you might ask yourself, wait a second, you just said that, but I'm not willing to accept it. I'm just say no, no, no. There's something fishy going on there in the background, maybe similar to the initial conditions. There's something about these electrons that makes them not all the same if they go for the first magnet and point up when you send them through the second magnet. There's something in there similar to initial conditions, something small, tiny, a hidden variable, something that actually predetermines if it's going to end up in the north or south state after passing the second magnet. So if I compare the truly random QM sequence with a pseudo-random classical sequence that we generated somehow, um, maybe they're both having the same type of randomness to them. If you think along those lines, you're not going to be by yourself. Similar reasoning motivated Einstein to coin this famous quote that God does not play dice with the universe. Einstein asked if a coin flip is deterministic, if you would just know precisely enough all the initial conditions, maybe there's something similar going on with the electrons. And if we would just be able to express that hidden information, some type of variable, some type of information, then we could predict deterministically that it will be in south or north. So this is sometimes called the hidden variable theory. The question is that a valid theory? Is that a theory that, we just philosophically can tackle, or is this something we could actually test? Well, it turns out this will become testable. And if you stick with the course after we learned the math for the test, then we can actually perform the test and see what happens. Not going to give away the answer yet. So, however, for your journal, I'd invite you to explain in your own words the difference, as far as you understand it, between the randomness in this quantum mechanical experiment with the spins going through two different magnets and the randomness that you get in classical mechanics, for example, from the coin flip. And then try to come up with your own opinion. Do you think there could be something like true randomness? And if it's possible to have true randomness, that means there are truly things that no one can know. You can't predict them. They're truly random. We don't know yet. We have to first measure before we can see it. Is that something we're willing to accept? Or do we follow Einstein's logic and say, no, 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 something like that would mean there is no one, no God, no anyone that could actually know about the future state? Are we willing to accept that or not? So just write out your own theory, discuss it with your roommates. I'd love to hear what you guys think. Okay, so is there actually any evidence for quantum mechanical effects that we can easily see? And we will do this in the classroom setting, but on the slides, I'll also try to run you from one very basic experiment that can actually show you this quantum effect. Most of them require elaborate setups, but this one here using polarization, you can very simply do yourself. What we're going to use for this is we're going to take polarized light, which is just the stuff we have around us. Great. And we send that light through a polarization filter. These polarizing filters, you can find them in your sunglasses. You can buy them online. I got some that I bring to lecture. They were like $5 or so. These filters, they have a grating on them that allows light to only come through if it is either if it is perfectly parallel to the axis of the polarization. So you can imagine it's like a grid, a grating that goes up and down, and only light that is up and down can go through. So if you have the randomly polarized light after passing through the filter, only the light that is polarized in the direction of the filter will be able to pass through. Okay. Very crude, but it will do for our purposes. Okay, so the direction of the light of ray after it passes the filter will have all the light perfectly parallelized. Great. So now let's do the experiment. Let's see, we have a polarization filter that sits up here, and the light that comes through is all polarized. Maybe this arrow indicates something. So it's vertically polarized like that. Now, if we take a second filter, and you might be able to tell that this background here outside of the filter is a little bit brighter than inside because this filter has taken out some light. So there's less light coming through here compared to here. If we now take a second filter that is polarized parallel to it, maybe just pointing the other way, the light that came through that way will also pass through this filter. And so the same amount of light goes through two filters as through a single one. Okay, that's fine. Now, if I take one of these filters and rotate it like that, and I only want to let light through that is polarized like this, well, this light has a part of it that can make it through this filter, but then there's clearly part of it that will be blocked. And so by taking the second filter and rotating it, we are going to get less light to come through. If I go to the extreme and I rotate it up all the way, then none of the light that made it through this filter can make it through this filter. It all gets perfectly blocked. And so you can see no light coming through the two filters here. Now, if I bring a third filter into the game, so I have my two that are vertical to each other, so no light can pass them, and I bring another filter in and I put it in front, well, there was no light that passed through the first two filters, so clearly nothing goes through this filter. If I take that filter, instead of putting it in front, I stick it behind the two filters, also nothing happens. So no matter what this guy does, the other two are going to block it all out. But something really interesting happens is when you take the third filter and you stick it between the two. Now I would like to have a third arm. And the third one that you stick in, you put in not in this or this orientation, but something in between. And if you stick it in there, you can actually, and we do that in the class, see the light turning on as you rotate it. So what you can see here is the two filters that by themselves were dark, you can see that in this corner, are becoming transparent again if you stick the third filter at an angle between them. Why is that? And what does this mean? Let's look at the quantum clock to see if that helps us answer this question. So remember our quantum clock, we can ask it, is it 2 p.m.? And it will say, yes, it's 2 p.m. or no, it's 8 p.m., but nothing in between. Let's ask it, is it 12 p.m.? So we're asking, is it up or down? 12 p.m. Yeah, the photon says it is. 50% of the cases, it's 12 p.m. Now, if we have a third filter that asks, is it 6 p.m.? So we have first filter and then another filter, and we ask it, is it 6 p.m.? Okay. The first filter asks, is it 12 p.m.? Half of them will say, yes, it's 12 p.m. If we only ask those that said it's 12 p.m., is it 6 p.m.? They will say, no, clearly not, because we already are 12 p.m. photons, not 6 p.m. ones. So 12 p.m. or 6 p.m. is the same as asking, is it 12 p.m.? Yes. Is it 6 p.m.? No, we already are 12 p.m. So everything is blocked. Okay. Now the idea is if we stick this other question in the middle, what will happen? So if we ask the clock, is it 12 p.m.? And it says, yes, it is. All of it is 12 p.m. And then we ask the 12 p.m. photons, hey, is it 3 p.m.? Then half of them will say, yes, it's 3 p.m. And half of them will say, no, it's not 3 p.m. If we take the ones that said, yes, it is 3 p.m. and ask them again, is it 6 p.m.? Half of them will say, yes, it is. So in the first case, where you only ask for 12 and 6, nothing passes both filters. So you see no light at all. And the second case, where you first asked, is it 12 p.m.? Is it 3 p.m.? So 12 p.m. gets you half of them. 3 p.m. gets you half of them. And then you ask for 6 p.m. It will give you half of those. So overall, 12.5% of the light will be visible. So this little polarization thing that we're going to do in class, and I showed you on the slide here, that truly shows that there is this crazy randomness going on where we're able to flip between two states, the 12 or 6 p.m., the vertical or horizontal polarization. We can flip between those. And if we do that in an interesting order, we'll be able to see very, very surprising results. And that's something you can actually show your roommates at home. It's very easy to do. You just get some of these polarization filters and stick them on top of each other. And that's truly an experiment that underlies and supports the theory of quantum mechanics. Okay, here's a question for you to think about. It's actually a pretty good lesson. You can also follow the link down here where I took that from. So we have here polarizers. The first one is oriented at 0 degrees. The second one is oriented at 90 degrees. And the third one is oriented at, so this one is 0, this one is 90 degrees, and this one is 180 degrees. What percent of light goes through P1, P2, and P3? So this is one of those questions that you can answer in your journal. We might discuss it in class, but work it through. You can also follow this link here if you want to find out. The first one is 0 degrees. The next one is 90 degrees. And then the last one is 180 degrees. So what happens as soon as two of them have a 90-degree angle towards each other? Shouldn't be too hard of a question. This image is not representing the problem. And this is just a representation, but the numbers here you need to use. Okay, good. Not going to give it away more. So, conclusion. We have seen that basic classical computing is made up of bits, and they can be represented as switches. And they are really great at approximating everything a human can do. Qubits, they need something else to represent them because they are not just in these clearly defined states, but in these weird in-between states that on measurement knock down into a specific outcome. And so spins and polarizations are possible ways of doing that. If you ever want to measure a spin, it's not enough to just say, hey, I want to measure it. You have to make a conscientious decision in which direction you measure. And the only outcome that you can get is, so if you have a magnet, for example, you can only get an outcome in the orientation of the magnetic axis, either north or south, 0 or 1. Those are the only outcomes that are allowed. And if you rotate your measurement device, you're going to get different outcomes, so maybe east and west, but there's still only two distinct outcomes that are allowed. But depending on how you rotate your magnet, you're going to get different outcomes. A really cool thing that we found out is already if we are able to just generate this one qubit or this one spin, we would be able to use measurements in orthogonal directions, like vertical and horizontally. And if we alternate those measurements, we can create completely random numbers, a series of random numbers. We think those are random numbers. We've tried to test them in various ways and never found anything that suggests that there's a hidden pattern behind them. So that's something that's completely impossible on a normal computer. That's quite cool. You can do that with a single qubit. In order to go now to the next level, and for example, tackle this question, is this randomness true or not? Is there some hidden variable? Is there something deeper about spins and photons that can explain all of the crazy things that we see? In order to understand that, we need to actually fill our toolbox a bit. And so next lecture will be completely devoted to linear algebra, but only that part that we need. So read the book, try to understand it, come back to lecture, watch the videos, and then do the problems in class. And I'm sure together we're going to get to a point where we will feel comfortable enough to make it through the next chapters in the book. I think this is the point where you need to decide if you're willing to put in some work. It's going to be reasonable, but it will be worth it. All right. See you next time.